Well, how are you doing? Okay, this is going to be a video about how an elevation angle is always a right angle triangle. Right? People are very confused out there. Surprisingly, on the flat earth side, not just on the globe side, they don't seem to realize that an elevation angle is called an elevation angle because the right angle triangle that it is pre-assumed. You don't It's like you don't buy a Volkswagen Passat and expect someone to tell you at the dealership that there's wheels on it. You know there's wheels on it. That's what a car has, right? It's kind of like that, right? The thing is this: if the elevation angle was just an angle, then it wouldn't be called the elevation angle. This here, right? This is the elevation. It doesn't matter if you measure it in degrees, if you use the units of inches, feet, miles, kilometers, meters, makes no difference. The point is that this is always, whether it be altitude or elevation, whichever way you want to describe them, both of them are straight lines. So someone's elevation, if they're on a mountain above sea level, is their elevation, right? That's a straight line above that point at sea level, directly below them, right? So if someone's elevation is while they're standing up on a mountain is 6,500 feet, then that means there's 6,500 vertical feet above that point at sea level, right? Mean sea level, whichever, right? The same for altitude. If a plane is at 38,000 feet, then its altitude is 38,000 straight line vertical feet above mean sea level. That's what it is. These things are not curves. They don't curve because you're using the arc scale. That doesn't change anything. They're still straight line, right? So a lot of people don't realize this, right? They think that because you must invoke, or they think that you must invoke a zenith angle, right, after you've measured your elevation angle to gain the distance along the adjacent, right? And they think that means that the elevation angle is not a right angle triangle. Some of them think that is why it's not, but they're wrong. It is a right angle triangle. You don't need a zenith angle at all, as I will show, right? I have here from this point, which is 0, to this point, which is 5,400, right? 5.4, it's 5,400. So imagine that to be 5,400 nautical miles, right? From this point here to this point here, right? Now, if we, and I have a 36-degree angle here, so, right, how do I determine the length of my adjacent without the zenith angle? Very simple, right? I measure my angle to be 36 degrees. That would be 90 minus, right, 36. Oh, sorry, that's 36, right, which is my angle, and I'll multiply that by 60, which will give me 21,600, right? All I do then is, right, subtract, right, 21,600 from 5,400. So then so 21,600, oh, what am I doing? Sorry, I'm doing this wrong. 54,000, right, minus 2160, equals 3240. So how did I gain the length of my adjacent without the zenith angle? Very simple. I just multiplied 36, my angle degrees, which is 36 degrees, by 60, and I subtracted that from 5,400. That's exactly the same thing. You don't need any zenith angle, right? So that gave me this length here, which is 3240, right? So as you can see, right, 3240. So that means my adjacent length here is 3240. Now in celestial navigation, that's all they're looking to know. They're not looking to know any more than that. That's all they're looking to know. But my point is, you don't need any zenith distance or zenith angle to determine that, right? So what's happening is it doesn't matter if my angle is 36 degrees, 84 degrees, or it's 11 degrees, which would put this celestial body here, let's just say, with and it would change the length of this down to something equivalent to something here. The point being is that as you're, like, literally, they're simultaneous, because you're measuring the vertical, you're measuring the altitude, you're measuring the elevation, so you're measuring the vertical. You can't deny the vertical, which is the opposite of the right angle triangle. You can't deny the opposite and still measure the vertical. You can't do that. You can't deny the opposite and measure the elevation, because that is the vertical. You can't deny the opposite and measure the altitude, because that is the vertical. So you can't deny, so when you're denying the elevation or you're denying the altitude, you're denying the vertical, which means you're denying the opposite of that right angle triangle. The reason it's called an elevation angle is because you're measuring the straight line elevation, right? Or solar, sometimes it's called a solar or celestial altitude angle. Same thing, you're measuring the vertical altitude. Right? Now, obviously, with a celestial body, they don't behave like a mountain or a light pole or whatever. So you can't, a building, whatever, you can't, so whatever height that you get to them is not their actual height, right? Because they don't behave the same as terrestrial objects. They're celestial, some things, I don't know what they are, but I know that they don't behave like terrestrial objects, so they don't, you can't say the height of this celestial body. If we base it off of the adjacent here, we can't say it's 2,354 miles. We can't say that just because this is 3,240 miles. But its apparent height at that moment, right, is 2,354 miles. That's its apparent height, right? And the apparent length of the hypotenuse is 4,004.86 miles. That's the apparent one. Obviously, because it's a celestial body, right, in 10 minutes' time, it will have a different height, even though you're in the same place. But the same, right, it will have a different apparent height, I should say, even though you're in the same place. Let's just say if that's moving away from you or moving towards you or whatever, right? Same is true, though, if that was like Polaris or whatever, and you moved away from it 10 minutes later, you're going to have a slightly different angle. Do you know what I mean? It depends on how far away you move. And then it's going to have a different apparent height. But that doesn't change the fact that as you're starting to measure, whether it be 1 degree, 4 degrees, 12 degrees, 36 degrees, you're instantly, as the measurement is happening, the whole triangle is basically, if you take this celestial body, you bring it straight down to this point here, right? The whole thing is just a straight line, right? It's just flat. What would happen is that if you bring it actually more down to this point here, right, the 5400 point, right, it's like, imagine this is a pole inside a tent. That this is a pole that as the angle increases, the pole, whether it be goes from 0 to 1 degree or 8 degrees or whatever, or 24 degrees or up to 36 degrees, that pole increases in length, and as that pole increases in length, this length here shortens. As that pole decreases in length, right, this length here lengthens, I should say. But the point is that this right angle is always there. You have this angle here, this right angle here, and this angle up here. So if this is 36 degrees, this has to be 54 degrees, because that's always 90. Because it's an altitude, an elevation you're measuring. So that means it's a vertical, so it's always 90 to the horizontal. So even if it's 1 degree, right, that you measure your angle to be, then you'll have a very small vertical over here, right, and a very long hypotenuse. But the point being is that you're still, as soon as you're away from 0, this is automatically employed. It's automatically created. It's part of the elevation angle. It's why it's called an elevation angle. They didn't call it the elevation right angle triangle or the elevation triangle because the triangle is employed within it, if you understand it. The same way as no one has to tell you that your new car comes with wheels. Of course it comes with wheels. It's a car. It can't come without them. The same way as you can't measure this elevation angle and ignore it as being a right angle triangle. That cannot be done. It is always a right angle triangle if it's only a quarter of a degree of measurement or if you've measured it to be 87 degrees, it makes no difference. All you're doing is changing the length of the vertical and the distance of the horizontal. And of course, the length of the hypotenuse. But that's all you're doing. You're changing these three lengths, but you're never changing what it is. So it's not a case of you measure just some angle and then you turn it into a right angle triangle. Or like the ballers do, idiots. They ignore this part completely. It's like, now I'm sorry, if you're a flat earther and you're ignoring it as well, then you're being an idiot. Because if you're ignoring this part, or you're denying the opposite, you're denying the elevation, you're denying the altitude, you're denying the vertical, which means you're not, it means that you're claiming you have a horizontal line, because you don't have any measurement of anything, because you're not measuring anything if you're claiming the thing that you're measuring is not there. If you're claiming the thing you're measuring doesn't exist, then you're not measuring anything. You're measuring the vertical, that's the point. So at all times, as soon as you start measuring this angle here away from zero, right, it's instantly a right angle triangle, because it's an elevation angle. There's no if, buts, or maybes about it. You can't get away from it. It's always got a 90 degrees to it. It's always got two angles. That's three angles. That's a triangle. As I said, they don't call it an elevation triangle, because it's implied that it's a triangle by the word elevation angle. You're determining a distance. It doesn't matter if you do it in the celestial navigation way, or if you do it in the ways that they would do it, like with a surveyor would do it, or whatever, with a mountain or whatever. It doesn't matter, like using just the angular size of the object, the known angular size, or the known distance to it, blah, blah, blah. It doesn't matter which way you do it. It's the same thing. I can take away these three lengths right here, right, and just have just pure triangle, right? And with 90 degrees, 54 degrees, and 36 degrees, it's still a right angle triangle. Makes no difference. It doesn't matter, right? What way you twist or turn it, it cannot not be a right angle triangle. Do you understand? It cannot not be a right angle triangle. Otherwise, it's not an elevation angle. This is so ridiculous that this has to be explained to people. But obviously there's people out there who can't get this. You can't measure the elevation and ignore or deny the elevation. So this star here will appear to go to here when this person is 5,400 nautical miles away from it, right? Sorry, this would be nautical miles. 5,400 nautical miles, right? So when that star appears to be, or when the sun, whatever, appears to be 36 degrees to their horizontal, that means its GP point is 3,240 miles away, and the apparent height, if you want, right, if you use that, although it's not part of celestial navigation, you can give links to these sides. It doesn't make any difference. It won't give you the height of the sun or star, because it doesn't. You can't give them a height. They don't adhere to terrestrial rules, right? But you can give them an apparent height. Right? The same thing though, like give them an apparent height. But what people don't realise is that, let's just say I'm measuring the angular height of a mountain, right? If I measure from here, and they say this is a mountain, I measure the angular height of it, right? And I don't know my distance to it. I don't know the height of the mountain. Does that mean that this is not then a straight line? That this is not a triangle? Does that mean because I've measured just the angle, does that mean that this is not a vertical? Does that mean that the triangle doesn't exist? No. That's a joke. Of course, it's always a triangle. It's an elevation angle. It doesn't matter if it's to a mountain, or a celestial top of a mountain, or a celestial body. It makes absolutely no difference whatsoever. Now, right, just to show, right, you can do this, right? Just so people are aware of this. You can do this, right? If I want to know the length of my hypotenuse, right, the length of this line, right, and the length of this one, I can use the length of this one here and the angle, 36 degrees here and 90 degrees here, to determine that that's 2,354 nautical miles. I said saturated earlier, I meant to say nautical. And this is 3,240 nautical miles. So then I can go, right, so what's the length of my hypotenuse, right? I can go, so 3,240 O, right, squared, right, plus, where is it, 2354, 2354, are we, squared, right, equals 160.38916, right, and we just get the square root of that. It'll be 4004.8615, blah, blah, blah. Point is, there is 4004.86. Point is, now I can do that, right? And just because they don't do that in celestial navigation, that they only want this length here, that doesn't mean that they're not using a triangle. I can still do that and determine all the rest of the lengths of the sides of the triangle, all that other stuff. And I can even use it then at a later date, believe it or not. Right? The point being is that, as well as that, firstly, you don't need the zenith angle. You can use that process, but you don't need to. You just multiply your angle here by 60 and then subtract that from 5400, same thing, right? So you don't need a zenith angle to determine the length of your adjacent. Now, if you want to use this or find this out, the length of this and the length of this, you then can. No one said you can't do it. No one said it's impossible. The point being is that it's not part of celestial navigation. They don't use those. They're not using this and they're not using this. They're using this. Sorry, this here. Now you can determine them if you want and get an apparent height to the celestial body at that time. So if I took an angle of 36 degrees, right, on November the 11th, 2025 at 7 p.m., right, from whatever position, right, then exactly 1 year later, right, if I'm out on a boat again and I see this exact star, right, in the distance at this exact date and time, I can then use the fact that it had a 2,354 nautical mile apparent height at that time, and I can use that as an angular size. I don't see why you wouldn't be able to use that as an angular size and gain a distance to it, right, at the time. So if your angle was, I don't know, to it was like 24 degrees or something, you could go, right, it has an apparent, at this exact time, it had an apparent 2,354 nautical mile height, right, and now my angle to it is 24 degrees, so that means that my adjacent length is blah, blah, blah. You can do that, right, but they don't do that in celestial navigation. But all that aside doesn't matter, because you can not have the lengths of these three sides and you still have a triangle. A right angle triangle, because that's what an elevation angle is, right? That's why it's called an elevation angle and not just an angle, right? So as soon as this here leaves this point over here, so when this, right, star or whatever that would appear to be at the horizon, right, leaves this point here, as soon as that happens, right, as soon as that leaves the horizontal, immediately this is being created. So as soon as you start measuring even 1/4 of a degree, immediately this vertical is part of that measurement. That's what's been, or sorry, part of that, because it's been measured. It's literally there. That's what it is. So you can't deny this part and then claim to be measuring it. You can't do that. That is contradictory. It's illogical, right? As I said, they don't tell you when you go in to buy a car, oh, well, there's wheels on that car. Well, there better be. It's supposed to be a car, right? That's the point of it. It's a car. It has wheels. You don't need to be told that that car will have wheels. You don't need to be told that the pizza will have mozzarella on it. You don't need to be told these things. It's a given. These things are a given. Do you know what I mean? The same way as people who actually do science don't need to be telling people that they use scientific method. It's a given. These things are just a given. So this right angle triangle is a given for every elevation angle, right? It's a given, no matter what, right? You can't measure elevation and ignore elevation. You can't measure altitude and ignore altitude. You can't ignore the vertical, because that's what you're measuring. And then you can't be ignoring the opposite or saying there isn't an opposite. When that's the thing you're measuring, this vertical is the opposite. It is the altitude. It is the elevation. It doesn't matter if it's in degrees. A Carpenter's set square is in degrees. It's still a triangle, a right angle triangle. Do you understand? There's no way around this. The ballers must deny this, because that ruins their ball outright forever. And as soon as flat earthers en masse cop on to what an elevation angle is and stop trying to help out the ballers and be idiots like the ballers are, then the problems will be far less for us. But unfortunately, flat earthers are listening to ballers, people who either don't know and don't understand, or do know and do understand and are being deceptive. So either don't know and don't understand, so they're ignorant, and flat earthers are listening to them, or they do know and do understand and are being deceptive, and flat earthers are listening to them. Stop listening to the opposition. They're not your friends. Listen to yourself. Listen to look at what's actually real. Because if you're denying that this angle here, has nothing to do with this, then you're not measuring that angle. Nothing happened. You have a horizontal line and that's it. And as I said, right, you can determine the length of the other sides. Who cares? No one's using them, but you can. And you can then use it a year later. Who cares? You don't need to do that. That's why we have celestial navigation. That's the point of celestial navigation, that you can use the triangle without using trigonometry. Right? You don't use trigonometry with it because all you have is the triangle. You don't have the lengths of sides, right? And all you want is this length, right? So, well, you do have the length of sides when you measure the triangle, but the point is that if you're just using just trigonometry and all you have is a 36-degree angle to the top of a mountain, and you don't know your distance from the mountain, you don't know what height the mountain is, then you can't do trigonometry. You can't do any of this. You can with celestial navigation after you've determined the length of this by multiplying your angle by 60 and then subtracting that by 50 from 5400. Once you have this, then you can determine the length of this and the length of this. But who cares? We're not using them. But you can if you want. It's not that you can't do that. It's people need to understand the difference. You're using a right angle triangle for your elevation / altitude angle in celestial navigation, exactly the same as you're doing it with surveying or anything else, right? You just, because you're using the celestial body to determine what you need to determine, you're not then looking to know the lengths of the sides. You just want the one side. But you can use them if you want. You can calculate them all. Calculate away to your heart's content. It's right. Calculate. Do it all day long. Nobody cares. It's not that you can't do it. It's that it's not necessary to do. But that doesn't mean that this and this are not there. Like, get some cop on, flat earthers. Stop being boneheads. Stop listening to the opposition. Because that's what you're being. And that's what you're doing. And it's only going to be to your own detriment. Because you're the one's going to look stupid. I won't look stupid because I know what I'm talking about. Because I don't deny the thing I'm measuring. It's like measuring the height of a door frame, then denying the existence of the door frame. Why would you do that? It makes no sense. You know, it's stupid. But look, what can you do? That's what people are out there doing. Right? But either way, it doesn't matter. Your elevation angle, or altitude angle, doesn't matter. It's always a right angle triangle. Because as soon as this right leaves that point, right, apparently, obviously, it's not really doing it. It's apparent, right, from the observer's position, and it ends up 1 degree above their horizon. Then straight away, right, instantaneously, right. And simultaneously, this is there. This exists. That exists. I've tried my out. That exists, and so this. I don't know how to make it any clearer to you. There's no way around this. It's always a right angle triangle because it can't not be. The same way as the car you buy from a dealership can't not have wheels and tires. Otherwise, you're not buying a car, are you? You know, it's not a car. Even if it has tracks on it, it's not a car. At that point, it's more or less a tank. Point being is that if it doesn't, like, no one, the dealership doesn't tell you, oh, the seats and that. Yeah, it's a car. There needs to be. It's a given. So hopefully this will somehow get the point across that you can determine the lengths of the sides, and you can do this, that, and the other thing, but you don't need to. And you also don't need any zenith angle. You don't need that. Just multiply 36 by 60 and subtract it from 5400. There's your length. No need for a zenith angle. You don't need it. You can use it if you want, and I know why they use it, but it's not necessary. Right? There's globe nonsense going on. Even though it's the zenith distance and zenith angle are right angle is another right angle triangle and a straight line distance. They hijack that. I won't go into it right now. Either way, right? If you say that when you're measuring an elevation angle that it's not a right angle triangle, then you're wrong. You're just wrong. There's no if, buts, or maybes about it. You're just wrong. It's like trying to deny the wall you're painting exists. This wall doesn't exist that I'm painting. How can you be painting it if it's not there? I don't know. Anyway, thanks for watching.